Hello friends, welcome for this lecture on grounded chair representation. Now friends, as I discussed in the last class, while deriving equations for translational mechanical systems, we had seen some of the spring mass dashpot systems in which we derived the differential equation of operation, and then we found out the transfer function for the same. Just to recollect, we had identified three types of basic elements. One was spring, which we represented something like this, isn't it? And this was the fixed end, it was having stiffness K, and this was subjected to a force F, and because of this force F, this was subjected to displacement X. When I pull this spring, the spring by force F, the spring will exert equivalent opposite spring force on it. And how we had written the equation? F was equal to K into X, isn't it? And how was the transfer function? Output was X and input was F. So X upon F was equal to 1 upon K. And what we had said, the block diagram, the input is F multiplied by 1 by K gives me X. So within this block diagram representation, I read from left to right. F into 1 by K is equal to X. F into 1 by K is equal to X. And this was output by input. We had called it as transfer function. Isn't it? And thereafter we discussed about a damper, which was represented by, this was a fixed end, if you remember, and this was subjected to force F. This is having damping coefficient B, and because of this force F, it is subjected to displacement X. And how was the equation for a damper? F was equal to, damping force is proportional to velocity. So F was equal to B into dx. What is this dx? D is nothing but d by dt. This we call it as operator form. Dx is nothing but velocity v. And the transfer function is equal to, what is the output? X is the output, F is the input, and the transfer function was 1 upon BD. And how was the block diagram representation? Input is F multiplied by 1 upon BD gives me X. This was the block diagram representation, and this is the transfer function. Just to recap, and finally, what was the third element? The third element was mass or inertia like element. mass or inertia element. So how it was represented? Mass M, it is subjected to force F. It will have the inertia force given as M into, and it is subject, because of this it is subjected to motion X, and because of X I have X dot velocity and I have acceleration also. So this force was given as M into acceleration, that is M into d2x by dt squared, and d by dt is d, capital D. So F was equal to m d square x, where d square x corresponds to d2x by dt squared, that is acceleration. And what is the transfer function? X upon F. X upon F was 1 upon md square. This is how we did the transfer function. And the block diagram representation was, input is F into 1 upon md squared gives me X. This was the block diagram representation for this mass. So these were the three basic elements we have used for writing the equation of operation and finding your transfer function and having block diagram representation. Now we had written equation of operation for a simple spring mass dashpot system by using Newton's second law. Sum of all external forces is equal to sum of all internally resisting forces. Now we are going to study a simplified method of writing differential equations for translational mechanical elements for bit complex mechanical systems, where these mechanical systems have multiple degrees of freedom. For single coordinate or single degree of freedom, our conventional equation writing is easier by using equilibrium method. But if you have got more number of springs arranged in series, arranged in parallel, more number of masses and more degrees of freedom, that method becomes a bit tedious. So grounded chair representation provides us a better understanding of the system, and equation derivation also becomes easier. Now, as the name indicates, before we get into this grounded chair representation, let us first of all try to recollect that this arrangement, as per Ravan's convention, we had called it as series arrangement. Though it appears as parallel arrangement, we had called it as per Ravan, F.H. Ravan's book, we had called it as series arrangement. This is subjected to X. If you recollect, we had called this, as per Ravan's convention, we had called this as the series springs. Isn't it? And what was the logic? Springs having K1 and K2, they will be experiencing same displacement. In series arrangement, they will be experiencing same displacement, whereas the force is shared by each of the spring, and each of the spring will share the spring force based on the stiffnesses K1 and K2. And we had called, as per Ravan's convention, parallel springs. Now, though visually they appear to be series springs, we had called them to be parallel springs as per F.H. Ravan's convention. Springs having stiffness K1 and K2 when subjected to force these as parallel springs as per Raven's convention. These will have displacements x1 and displacements x2, and overall displacement was said to be small x, and small x was summation of x1 plus x2, isn't it? Now, what is the typicality of these parallel springs? Force acting on each of the springs is same. I repeat, force acting on each of these parallel springs is same, whereas displacement is shared by each spring. Whereas in these series springs, displacement was same and the force was shared. In parallel springs, force is same and displacement is shared. And what we had said, we had called for these series springs, equivalent stiffness was given as simple sum of K1 and K2, whereas in this parallel case, 1 upon K equivalent parallel, 1 upon K1 plus 1 upon K2. That was nothing but K1 into K2, K1 plus K2 upon K1 into K2. This is 1 upon K equivalent, and K equivalent was inverse of this, K1 into K2 upon K1 plus K2. So this is just revision of series springs and parallel springs. Same logic applies for the dampers as well. Now in grounded chair representation, we call these stiffnesses and damping coefficients as mechanical impedances. Okay. So before we get into grounded chair representation, some rules we have to follow. Okay. So what is the first rule? Ground at the bottom and second, so whatever is the arrangement, even if I have got spring mass dashpot arrangement wherein ground is shown at the top and the force is acting downwards, here in the grounded chair representation we have to convert that arrangement into by showing ground at the bottom. Second important rule, identify number of coordinates. Coordinates means degrees of freedom. Degrees of freedom. How many motions are there? x1, x2, x3, x, y, z, w, whether it is one coordinate or it is a single degree of freedom system or 2 degree of freedom system or 3 degree of freedom system. Accordingly, we have to draw equal number of lines. Equal number means equal to degrees of freedom. Number of lines corresponding to degrees of freedom. Equal number of lines. If I got two coordinates, I have to draw two lines. How will it will look like? Suppose I draw ground at the bottom. If I got x and y as two coordinates, so I draw two lines corresponding to x coordinate and y coordinate. Third important rule in grounded chair representation is the coordinate at which force acts, the coordinate at which force acts should be, this is very important, should be at the top. While solving the problem, we'll understand this. Wherever the force is acting, that coordinate should be at the top. So in this case, if force is acting at y coordinate, that y coordinate should be at the top, and I show the force on this grounded chair representation. And thereafter, next important step, insert the components, that is spring, dashpot components or elements. What are these elements? Either the mass, spring or damper. Insert the components or elements between the coordinates. And finally, write equations. So shall we repeat? In grounded chair representation, ground is always at the bottom. Ground is always at the bottom. Then identify number of coordinates, number of degrees of freedom, draw equal number of lines. If I got 3 degrees of freedom, 3 motions, then 3 lines I will be drawing. In this case I have shown 2 lines representing 2 coordinates. Then this is very important step. The coordinate at which force acts should be at the top. The coordinate at which force act should be at the top. If the force is acting on x coordinate, this x will be at the top. This is how I have to arrange the lines. Okay. Then once I draw the ground line, once I draw the number of coordinates, once I show the force in between, I go on inserting what are the components in it. And then insert components, elements between the coordinates, and finally write the equations. Okay. I think we'll stop for today, and next class we'll take up one small problem and then understand how this grounded chair representation can be used for drawing this grounded chair diagram and thereafter writing the equations of motion. Thank you.